Hi there and welcome. We are continuing our discussion of advanced features of SQL. Greetings from the Falcon cockpit. It's time to enter the chapter 05, which is the chapter on window functions. You will see that this is one of the more substantial, longer chapters, and for a good reason, because window functions are a really exciting, a very expressive feature that can help you to express really complex computation in terms of really simple, very well readable, and very concise SQL queries. Window functions are a rather recent addition to the SQL standard, and they are not that well known outside the SQL experts realm. So we are really entering the advanced SQL stuff by now. So let's see what's going on with window functions. All right. So only with SQL 2003, the new ISO SQL standard 2003, we introduced a new mode of processing data inside a SQL query. There were established modes already, and we have talked about all of these already. The first three rows in this overview of this table. So you can of course apply functions like arithmetic operators to the rows or the row values that you have in hand in a SQL query, and that would map that particular row argument value to another value, maybe to another row, maybe to another scalar value, but a row would be mapped into one other scalar value or another row. Okay, so that would be the normal operation of functions. There are, of course, other functions, the table generating function or the set returning functions that we have talked about. You would provide a particular row as argument, and out of such a table generating function would come an entire table of rows over which we then can iterate. So generate series would be one example of this. You specify some row or some really simple scalar parameters, and from that an entire table of rows is generated over which we then can iterate. All right. And then there is, in some sense, the converse. We can feed an entire group or bag of rows into an aggregate function, and what comes out of it is one row per group. One row is the result of the aggregation of an entire group of rows. So an entire group of rows is reduced to a single aggregate value. And that have been the modes of computation that we have seen so far. And we will now add a new mode of computation, and that's the window functions. And the entire focus of this chapter is on this last mode, on this new window function mode of thinking about computation in a SQL query. What we will do now is to look at a row and its vicinity. Some rows before and some rows after that particular current row. And take this vicinity as an input to a function, to a so-called window function, from which this function will generate one result value, one row result value. Okay, so the entire vicinity of a row. However, that vicinity is defined in very flexible and really intricate ways, as we will see. So the entire vicinity is visible to the window function. Some context of the current row is visible to the window function before it does its job and computes a result. This is really powerful to talk about the vicinity, the context, the surroundings, the neighbors, whatever you want to call it, of the current row. And this really makes a difference when it comes to the specification of complex computation. This is an entirely different view of computation than this view, which has a very narrow view of the current row only. It's different for window functions. We are in control what the context, what the vicinity of the current row is. Okay, so window functions are indeed row-based. So for each row, we will individually decide, hey, what's your vicinity? What are your neighbors? And for each row R, we will compute the value of the window function. Okay, so each row R will be the current row at one time. We will look at its vicinity and compute the window function result. Okay, this is what's just said here on the slide. Okay, so a bit a bit deeper. Let's zoom in there. So that would be a table of data we want to compute our query over. And as you can see, all of these rows, I've assigned row identifiers to all of these rows. These are virtual row identifiers only introduced for the purposes of these slides, so that I can more easily refer to a particular row and can point you to the row 7, and that would be this particular row. Let's focus here. This would be the row 7. It's just an identifier. It's not stored in the input table. It's just a means to refer to rows in a simple and efficient fashion while we talk about the window function stuff here. Okay. As I told you, window functions are row-based in the sense that each row of the input table will be the current row at one time, the row in focus for which we will determine the vicinity. And in all of these slides, I will mark this current row using these striped symbols. So currently row 4 is the current row that we are looking at. Okay, so we will now look at row 4, but also the vicinity, the neighbors, the context of row 4. And such context in these slides I have depicted with these dashed frames here. I've used several types of dashes when we talk about several frames in one slide. But I will always use this metaphor of using these dashed frames to indicate the vicinity that's currently under investigation for the current row. You see that within that particular vicinity is the current row itself. All right, so some rows before that and some rows after the current row might be in the vicinity that we are currently considering. Okay, there are different modes, as I told you already. There are different modes on how to define or how to identify the rows in the vicinity. Which rows are considered the neighbors, which rows are considered the context of the current row. All right, we will look at all three of these. They are subtly related, but they differ in detail. So the symbols would be the rows windows, where we just look at the current row and then count backwards and forwards, like 3 rows before, but only 2 rows after would be considered in the vicinity of the current row. All right. There would be other ways to measure or to identify the vicinity. There is methods that look at particular values in the table to measure the distance from the current row. And so it would not be a position-based vicinity, but a value-based, distance-based vicinity that we are considering here. And there is also groups, windows, or modes of vicinity detection where we look at groups of rows that share the same identifying value. So it's much like grouping in a sense, but let's talk about this in detail when the concept is in focus and we have an extra slide to talk about that. Okay, so each row can be the current row at one time. So while we walk the table, while we walk the input table, every row will be the current row at one time, and the vicinity that we've defined will slide with the current row. So the vicinity wanders, walks with the current row, and will always contain the current row and maybe a bit more. Okay. As you can also now see is that the semantics of these window functions, or the semantics of the vicinity rather, is really dependent on a row ordering. It only makes sense to talk about the vicinity, the neighbors, the context of a particular row if there is a well-defined order on the rows of the input table. All right? So this is the current row, and this is the row before that. There must be some ordering criterion that really orders the row in the table so that it makes sense to talk about rows that are distinct from the current row, that are close to the current row and thus belong to the vicinity. There must be an ordering criterion. So almost all of the examples that you will see will talk about a well-defined row ordering. If this row ordering is absent, then vicinity will be non-deterministic and arbitrary. So we will always talk about the well-defined row ordering when it comes to such row vicinity. And as you see here, there are different notions, different vocabularies on the table when we talk about this vicinity. Other names would be the frame around the current row, so that would be the frame around the current row, or the vicinity, or the window around the current row, and that would be the source of the name of the entire discussion here, window functions. So vicinity, window, frame, neighborhood, context, I think all of these will be synonyms while we discuss this stuff here. Okay, so let's look at the first mode of detecting who is in the vicinity, who's in the frame around the current row. Okay, we will first talk about the rows mode. All right. And here you can see the syntax that will be shared by all of the rows, the range, and the groups mode of frame computation. They will only differ in the choice of this particular keyword here. So currently we are in the rows mode. All right. It's of course our purpose. It's of course our purpose to compute a function over the rows in the vicinity inside the frame. And this would be the function that we are computing, the window function f here. All right, we will talk about these window functions in due course, but we will, in the next few minutes, we will focus on the vicinity of the frames itself. How are the frames determined? Once we've determined the frame, then it's time to compute the window function over the particular frame. But let's decouple the discussion here. Let's first focus on the frames only, on these guys, and then later talk about the variety of cool functions that we can use to compute over these frames. Okay, as I told you, row ordering is super crucial for these window functions, and this is the ordering criterion that we will need. So that would be just ordering criteria, just in a normal order by clause in a SQL query. Some expressions whose values we will use to order the rows inside a table. Okay. And then you can see this over keyword here, which really is the distinct keyword, the distinguishing keyword for all this window function functionality. This introduces the whole window-based mode of computation. Okay, there's more stuff that can go inside these parentheses, and but let's take it step by step. So we will add more specifiers that we can add inside these parentheses to be even more precise about what makes up the vicinity of the current row. Okay, so in rows mode, how could these frame specifications look like? How do we define frames? Okay, so that would be our table, and the rows of the table are indeed ordered. I've specified this, or I've indicated this using this particular arrow. So the rows, row 1 to row 7, are ordered already according to these ordering criteria. Okay, this is the current row. This is the current row, and I have specified or indicated 3 different frames around this current row. This would be the first frame. This would be the first frame. Let's talk about this frame. We specify its borders, so its first border and its second or last border, in a sense, by using this between phrase. All right. So from the viewpoint of the current row, this frame extends to the very beginning of the table. So it's unbounded preceding. We are looking from this row, we are looking behind us in unbounded fashion until the beginning of the table. This is the meaning of unbounded preceding. Okay. From the viewpoint of the current row until the beginning of the table. This would be the meaning of unbounded preceding. And the second border would be the current row. All right. So between unbounded preceding and the current row, this would be the span of the frame that is specified here. Okay. And you can see the rows inside the frame. I've listed them explicitly here. So from the beginning of the table, from row 1 up to row 4, which is the current row currently, that would be the span of this particular frame. A different frame would be this frame. it extends from the current row until the end of the table. Okay, so it would be between the current row and unbounded following. Everything following the current row, following, of course, according to these ordering criteria. All of these rows would be considered the vicinity regarding this frame specification. So this is a different frame specification, and we have already specified two different frame specifications here. So of course only one of these may go in the place of the frame specification here. I'm using this slide to depict more than one possibility of computing frames, just to keep the exposition compact here. Okay. So row 4 from the current row till the entire end of the table, row 7, that would be in the scope of this particular frame. Okay. The third and last frame depicted on this slide is this frame. Okay. And of course it includes the current row, but it starts one row position before the current row and extends 2 row positions after the current row. Okay, now it really becomes super crucial that rows are ordered, so it makes sense to talk about the one row before the current row and the 2 following rows in the ordering criteria, in the ordering specified by the E1 to En expressions above. Okay, so row 4 is the current row, but row 3 would be included, and row 5 and row 6 would also be included because the 2 following rows are included as well. And that would make up this particular window around our current row. So the distance from the current row is just measured in the number of rows before and after our current row. This is the meaning of the rows specifier. The distance from the current row is measured in the number of rows before and after our current row. So that would be a third possibility for a frame specification in the rows mode. We will see countless examples throughout the lecture, but you can see this is rather intricate already. So yet another mode of vicinity specification. It would be the range mode. All right. So everything is the same actually, but we exchanged the rows keyword for the range keyword here, indicating that vicinity computation will now be based on a slightly different mode. All right. It's a requirement when we use the range frame specification that we use a single column A as ordering criterion. Okay, so range frames always go with a single column range ordering criterion as specified here also in the sample syntax. And of course, this is the row. This is the column A that we are using as ordering criterion. And the rows here are indeed ordered in ascending A order currently. Okay. Of course, anything could go here. We could also order by A descending. That's fine. But a single column has to be the ordering criterion for the range mode. Okay. So how does vicinity computation work now? So of course, one of the rows will be the current row. In this sample table, row 3 is the current row. Okay. And now the computation or the determination of the windows around the current row is based on the distance, based on the difference between the current A value, which is V2, as you can see here, and the A values of all the other rows. A row whose A value is not too far from the A value of the current row would be inside the vicinity, inside the frame. Okay, so rows whose A value is not too far from the A value of the current row are inside such a range frame. Okay, so let's see. This frame extends from the current row until 2 following. And the 2 following here means any row whose A value is at most 2 larger than ours. Whose A value is at most 2 larger than ours would be considered inside the current frame. Okay, so you can see this is the frame I'm currently talking about here. Okay, and it has to be that the v3 value, this v3 value, is indeed has a distance to our current a value v2 from at most 2. All right, this row is not included in the frame, and we thus know that the difference between v4, its a value, and v2, the a value of the current row, has to be larger than 2, so it's outside the range frame. All right, all rows sharing the current a value with our current row. The a column doesn't have to be a key, it's just the ordering criterion. So there's a whole group of rows here that share the a value with our current row. They would also be considered part of the frame. They are the peer group of our current row. Regarding the a value, they cannot be differentiated. They are in the peer group of the current row and would be considered part of the frame. Okay, this is also the case if we have a specification like this. Between unbounded preceding and current row. Unbounded preceding, we have seen that before. So the frame extends from the very start of the table until the current row. And the current row is row 3. But its peer group will always be considered when we construct the frame. So the frame indeed includes row 4, and this would be the frame that would be considered by this frame specification. All right, so in the range frame specification, the rows of the peer group of the current row will always be included inside the frame. Okay, so it's the distance of a values, the distance of values inside this one particular column that decides the membership in the frame. And that already explains why we are insisting on a single ordering criterion here, because we are measuring the distance with respect to this particular column with the values in this column. And that's only easily done if this ordering criterion is a single column, so that we can easily compute these differences here. Okay, that's a quite different row. So the rows mode is just looking at the position of rows. The range mode is looking at the distance or the difference of values, of a values in this particular case. Last mode of window frame specification is the groups mode. All right, and this would be the indicator, the syntactic indicator here. All right, we can go back to an entire range of ordering criterion back here in this mode again. All right, now it's really about groups of rows that share the same ordering criteria. All right. In this case of this particular table, the ordering criterion again would be column A, and you can see that some of these rows here share the A value. Regarding the A value or this ordering criteria, they could not be differentiated, so they are considered members of one group. Okay, so if this is the current row, then of course, just in the range case, this current row would have its peer group around it. It would be the V3 peer group that is considered here. But there would be other groups. There would be groups of rows before our current peer group. It would, for example, this is the V2 group. It would be one group of rows consisting of 2 rows that would make up the V2 peer group. It's the group directly before the current row. And there's also groups after the current row. You see that this row with its V4 value will make up a group consisting of one row only. That's a very tiny group, it's still a group. And again, this last row would be considered a single row group. All right, so now frame inclusion or frame membership is just determined by the number of peer groups before and after the current row. Okay, so we are not counting individual rows like in the rows mode, but we are counting entire groups of rows. Okay, so between one preceding and one following concerning this current row would consider the one group before our current row and the one group after our current row. Okay, so this would be the group before the current row. It would be included in this frame. This would be the group after the current row. It would be included in the frame. So the entire frame is what we've seen specified here. Okay. So really this is the key phrase here on this slide again. It's the distance measure that we are using to determine vicinity or neighborhood in the groups mode. And here's another frame specified. It includes the current row, and with the current row really go all of the members of its peer group. All right. And then we extend the frame until unbounded following, so to the entire last row in the table, which is row 7 in this particular example. This would be the extent of this last frame specification that we are considering on these slides. I know that these slides have been really dense and lots of stuff is in there, and the difference between rows, range, and groups might sound subtle, and it is indeed. We will find use cases for all of these, and I have examples with me that will show the subtle difference between these in a minute. The window function syntax is rather verbose, right? What is common in SQL that for many common idioms, many common situations that we will use again and again in queries, that SQL defines abbreviations. And there is indeed some abbreviations that are related to window functions. There is one particular nice abbreviation, which is the over and then empty parenthesis abbreviation. You see no ordering specification here, no frames, groups, whatever mode. It's not needed in this case because, as you can see, the entire table would be considered the vicinity of the current row. Each current row would be placed in a vicinity that contains all rows of the input table. This is really interesting because this means we can compute the compute aggregate-like functionality for each row individually. So this is really something else. You will see in an example in a minute that this is really interesting. So before this window function computation mode, we could of course evaluate aggregates, but there would be one aggregate computation for the entire table. Now we can compute aggregates for individual rows, for each row individually, and that's quite interesting and sometimes quite powerful. All right, so the frame is all of the row contents. There is no need to specify any row ordering. Any row whatsoever will be included in the frame anyway. It's different for this abbreviation, which is really syntactic sugar for this longer specification here. All right, it's only the order by a single column specification, and this means the same as order by A. All right. And then building a range frame from the start of the table until the current row, until the peer group actually of the current row, because we are talking about ranges here. All right, so the frames will always start at the beginning of the table and then extend until the current row and its frame, actually its peer group. Okay, so if row 3 is our current row, row 4 would be included in this one particular frame. It's like looking at the current row and everything that came before it, looking back until the maximum point in the past when the scanning of this particular table happened. We are always looking back from the current row until the very start of the table, because this is something that is happening quite often in computations that are called so-called scan computations. This is something that comes up all the time in algorithmics. That's why we have this handy abbreviated notation in SQL here. All right. Still, these frame specifications may be rather wordy, And as we will see, if we compute more than one frame specification inside a query, we will find ourselves to repeat the same window specification, the same frame specifications over and over again, the same ordering criteria again and again. And that can become really tedious and quite error-prone, actually. That's why there is the possibility in SQL, and it's just syntactic sugar, as we've indicated here, lollipop. It's possible to name window frame specifications. So name the frame, in a sense. Name the frame specification and then only refer to this very compact, hopefully self-documented name when we are invoking window functions. And we, instead of repeating the same window specification, super wordy, super long specification again and again, we would just refer to the name. All right. And this is actually introduced, the names are introduced using this window clause, which is situated syntactically at the very bottom of such a select from where block. You see it's located just before the final closing order by clause that your queries might have. Okay, so we would introduce such names here like W1 and maybe many more up to WN, and they would stand in for these frame specifications, frame 1 until frame N. And once these are defined, in the rest of the query, we would be allowed to specify frame specification just by referring to these compact names here. And they would stand in for the potentially complex frame specifications listed down here in the window clause. Of course, many window functions like the F and the G window function, they may refer to one window name like WI multiple times, right? So we would save ourselves from repeating these window specifications. Name the frame makes the formulation of window queries more compact and less error prone to edit. Okay, so lots of talking now, lots of slides. It's really high time to show you the window function computation mode in action. And I will do this, and I will propose to just use SQL itself to explain the window function and the frame specification semantics to us. All right, so to do that, I will use this particular table here. It's table W, one of the playground tables that we're using in this lecture. It's just another playground table. You see that it comes with the column A that we will use as the ordering criterion. Okay, it also has some other payload data that will become interesting when we introduce more features even in the course of our discussion here. And I've also introduced a column row here that indeed materializes or really explicitly stores the row identifiers, row 1, row 2, row 4, as we've seen them on the slides. Again, this is only for illustration purposes here, so that we can easily tell, for example, the rows row 3 and row 4 from each other because they are sharing the same A value. So regarding the ordering, they would be considered the same or in the same peer group, but of course they are individual rows, and this key here, the row key, this row identifier would allow us to tell them apart still. Okay, over this very simple table W, we would execute queries like this. Okay, we will of course iterate over W. I will play with different frame specifications here. Okay, I will just name these frames win so that I can refer to the symbolic name in the rest of my query. And then I will just have a select clause that lists the current row. Okay, this is the current row in focus, the row around which we compute vicinity. Then I will perform a count over the current frame. And as you can see, indeed, normal aggregation functions appear to be valid window functions, and indeed that's the case. And you can already guess what the semantics will be. If we have computed the vicinity around the current row regarding this window specification, and there is a number of rows in the vicinity, count star will count the number of rows in the vicinity. So this count star really only has an effect on the current vicinity, not on the entire table, for example. And it's the same with all the other aggregate functions. ArrayAgg, the very well aggregate function that we've seen so many times now, can also act as a window function. It will aggregate these values. It will aggregate these values over the current frame. Not the entire table, but the current frame would be the scope of the aggregation. And you can see what I'm aggregating here. I'm just aggregating the row identifiers here. So I can see an array of all the row identifiers inside the current frame. It will make the current frame visible in a sense, where you can see the explicit array of row identifiers that are considered to be part of the current frame. That's a very compact and nice query, and if we play with this frame specification, we will see how the count and of course the number of rows inside these frames will differ. Of course, this count here is just the length of the array of rows that we are aggregating inside the frame. Okay, now it's time to switch over to the terminal, and there we go. Okay, so let's just create this W table. Here it is. It's just that table. And it's empty currently, but I will insert 9 rows here. 9 rows with A values that we will use as ordering criteria, and some other payload that we will not consider too much in the next few minutes. Okay, there we go. 9 rows inserted. Okay, so let's start with our first query. And the first window specification, the first frame specification that we are using is just the empty parenthesis. So if we are looking over here where we use this window specification, it just stands in for the empty parenthesis. So what we have here is really the same as this. Okay, so we are using the syntactic abbreviation that over the specification with empty parentheses, which means all rows of the table W. All rows of the table W are to be considered part of the current frame. Okay, we don't need any ordering specification, just makes no sense. All rows of the current of the table are considered part of the current frame. So let's see what's the result here. Okay, so we see 9 rows in the result. That's no surprise because the input table W had 9 rows. Each row of table W can be the current row at one time, and it indeed is. You can see that the current row is listed here in the very first column. Each row, each of the 9 rows is indeed at one time the current row. All right, the frame specification is including all rows of the current table. So the size of the number of rows inside the frame is always 9. All of the rows, all of the 9 rows are part of the table, and indeed we can see all of the 9 rows are indeed part of the table, or the frame. And it's the same for all of the rows that we have been iterating over. Okay, so this is the effect of this over empty parentheses window specification. Of course, we could use other aggregate functions. We could use other aggregate functions, not just the count and the ArrayAgg, to and evaluate them over this very simple window specification. So we could perform a sum or a max computation or a Boolean universal quantification, looking for this predicate that tests whether all bool and whether all b values are indeed this black circle. And they aren't, as we've seen in the sample data. And this same aggregate computation would be performed for all the rows of the W table. So let's see, we should see identical results for all of the current rows. Again, 9 entries. Each row has been the current row. I've listed the A value, and I've listed the values of the aggregates that we have computed. The maximum A value over the entire table is 7, of course. The sum over the A values over the entire table is the same for all the current rows. It's just 35. If you sum up these guys, it should add up to 35. And the outcome of the universal quantification is false for all of the rows because there is, I think there are some white circles inside somewhere in this table. Okay, second example. Now the over order by w.a. So the over order by only also constitutes some syntactic sugar, and it actually stands in for windows that start from the very beginning of the table and then extend to the current row in its peer group. Okay. So let's just do that and make the frames visible again. Make them visible again by counting their size and then also explicitly listing the members of the current frames. Okay, now it's really crucial to talk about a particular row order. Otherwise, it makes no sense to talk about the first row, the second row, up to the current row in this table. We need an ordering criterion, and it would be just the column A. This down here is just for presentation purposes. You may very well delete this particular phrase. It will not affect the computation of the window in any way. The ordering specification is this. This is the relevant ordering specifications for the window computation. This is just for illustration purposes so that we can see the rows in a very well-defined order. Okay, so let's see the behavior of windows that extend from the very beginning of the table up to the peer group of the current row. Okay, so if the current row is the very first row, then there is not much before that, and it would be just this row. But already for the second row, we would of course include the current row in this frame, but everything before it, the row 1, for example, would be included. The following 3 rows all share the same peer group. You see that their A value is identical, so they're all in the same peer group regarding this window specification. They are all treated the same. Okay, of course, row 3 is considered with its peers, row 4 and row 5, and everything before row 3. Row 4 is considered with its peers, row 3 and row 5, and everything before that, and so on and so on. Okay, and so it extends. The last row is of course included in its own frame, and everything before that last row would also be seen in the current frame. It's really looking from the viewpoint of the current row backwards to the very beginning of the table, and everything would be in scope in the current row and could influence a computation that we are performing for this one particular current row. Okay. We could do the same, but switch from range mode to rows mode. There is no syntactic shorthand for that, but we could just explicitly expand the row specific or frame specification syntax here and do the same in rows mode. Go from the unbounded preceding from the very beginning of the table until the current row. And that's what I've done here, as you can see. Okay, and now peer groups play no role. Now it's really about the current row and everything that's before it. Okay, the current row and everything that's before it. All right. Okay, and so we have a really nice increase, in the frame sizes as we walk along the table and approach the last row, which will of course see itself in everything before it. All right, so this already looks very useful to me in having the possibility to talk about the current row and everything that came before it, in a sense. We will see many applications of that. Very interesting. All right. We could, for example, compute a running sum. The A values summed up, for example, up to the current row. So starting from the beginning of the table, add up all the A values until the A values seen until the current row. So the A values seen so far, in a sense. And that's why I've chosen this particular name of the column here when I'm computing the sum aggregate. Okay, And I'm again using the rows mode of frame specification. So each row is considered individually here. And if we do that, we find that the A sum so far is seen here in this last column. Looking at row 6, for example, the A sum so far has been 16. So 1 plus 2, 3, 6, 9, 12 plus 14 is 16. Yes, that's the current sum of A values that we've seen so far. Okay, it's computing the running sums, and running sums computation is a building block in many algorithms out there. All right. And now one example for a window in which we are using the between natural preceding and natural following. So we have some real numeric specifiers here. And since we are operating in rows mode, we know that the 1 and the 2 are really to be considered as numbers of rows. So the windows here will normally include 4 rows. The current row, the 1 row before that, and the 2 rows after the current row, which makes up 4 rows. Okay, so what we expect to see as frame sizes would be 4 rows for almost all of the rows, unless we are at the beginning or at the very end of the table. At the very end of the table, there might not be 2 more following rows. At the very beginning of the table, there might not be a preceding row. And we will see that in the forming of the frame specifications. Let's see that. Okay. So if you're at the beginning of the table, then there are two following rows. That's fine, but there's no preceding row. Okay, so the entire frame only consists of 3 rows. In the middle of the table, there is indeed the possibility to talk about 1 preceding and 2 following rows. Okay, so here from the viewpoint of row 4, there's 1 preceding row, row 3, and 2 following rows, row 5 and row 6. And once we approach the end of the table, then of course there are no 2 following rows and the window or frame sizes decrease here. Okay. Also a very nice way to talk about the vicinity of rows in a very controlled fashion. We could use that, for example, to do some smoothing of the A values. Use the vicinity, the 1 before and 1 after row vicinity of our current row. Consider all the A values inside the vicinity and compute the average of the A values. And that average would be the new smoothed A value that we assign to the current row, and that would be the result. Okay, so smoothing around this value, looking at the row before and the A value after it, it's just all about 3. So the smooth value itself would be 3, but you can see that the smooth A value incorporates the following and preceding A values for each current row. So that would be some smoothing going on in a vicinity of size of rows of 3 rows. Okay. Finally, 2 example queries that help you to appreciate the difference between the range and the groups frames. Okay. So let's consider the current row and consider a range frame around it that extends from the current row. It also includes its peer group and 2 following. And 2 following, if we are in range mode, means every row is included. Every row is included unless it's the difference of its A value is too larger. It's larger than 2. The difference between the A value of the current row and that following row is larger than 2. I'm sorry about that. Okay. So if that difference is larger than 2, then that row is not considered in the vicinity in the frame anymore. If it's less than 2 or at most 2, then that row will be included in the vicinity. So let's see whether we can indeed see that. Yeah. Okay. So let's look at this particular row here, at the window around row 5. Okay, and the window around row 5 includes row 6, and that's this guy, because the difference of its A value 4 to our value 3 would just be 1, and that's within the range of 2 following. This row 7 here, with its A value of 6, would have a difference to the current A value 3 of 3. That would exceed the admissible row A value difference and would thus not be considered part of the frame. So looking at this row again, the frame ends with the row 6. Okay, and you can explain these frame sizes for each of the current rows if you follow this this train of thought. Okay, if we repeat the same experiment using groups frames, then we would consider vicinity in the number of peer groups before, okay, we are looking at only at the current row, and after the current row. The number of peer groups after the current row. All right, so let's see what's happened now. Okay, if we look at this row 5 again, just as we did in the range example, okay, here we see row 5, of course, included in its own frame. And now we see row 6, row 7, and row 8 included. All right. So what about the peer groups? What about the peer groups after the current row? That would be one peer group here. The peer group defined by the A value 4. Okay. That's one peer group away, one peer group following after the current row. It would be included. This is another peer group. It's the peer group defined by the A value 6. Okay. This group is 2. This peer group is 2 groups away from the current row, and it would also be included. All right, because we are looking at 2 following peer groups. This peer group, single row peer group, is too far apart. It's 3 peer groups apart from our current row and would not be considered to be part of the current frame. Okay. So this is I think this must be the longest video that we've shot in the course of the Advanced SQL course now, and I want to apologize for that. But I think it was worth it because we now have all the basics of the frame specifications of these really flexible rows, range, group specification that we can use to specify row vicinity. We all have them in one place now. You can refer to this one particular video and the samples in the window functions file. I hope you find that useful. The use cases, the number of cool situations in which we can use window functions for good measure are countless. And I hope you'll be around when we start to discuss these in the upcoming videos. See you then. Bye-bye.